All right, let's get started with today's material. Let's quickly recap. What was the last chapter on that we just did?
Similar triangles.
Similar triangles. That was the heart of the chapter. And we went over our three basic ways that we determine if two triangles are similar. What are the three basic ways?
One of the angles are congruent and two of the sides are proportional.
Yeah.
That's one.
So accidentally going to draw congruent triangles. All right, so if these two triangles are similar, one of the things that we would know is that, well, one of the ways we can test is if this angle is congruent to this angle, and big A over little a is equal to big B over little b, if those are the lengths of the sides. The sides are proportional. That was one way to check. How else could we check?
All of the angles are.
All three angles are congruent to each other, so this angle is congruent to that, this angle is congruent to that, and then the remaining angle is congruent to the remaining angle.
It can just be three angles. Or two angles.
Now, it is sufficient to just have two angles congruent rather than all three. Because if two are congruent, then the third one is also congruent, because the angle sum of a triangle is a straight angle. We'll define degree almost in the last chapter that we covered.
I was actually going to ask about that. So in the book, it says that that's one of the
Corollary?
Corollaries.
It said it was one of those, and then it also just seemed like it didn't want us to assume that they were similar when they were two congruent triangles.
No, that's exactly what it wants you to assume.
Really?
Yes. So a corollary is a quick, simple proof that almost follows for free.
Yeah.
So three angles being congruent because that's probably what you were told through most of your math education, and then the author saying, in fact, we just need two and we're good.
Yeah. Okay.
So two is sufficient. And then finally, what was the last way?
All three of the sides are proportional.
All the sides are proportional. So that means that big A over little a is equal to big B over little b is equal to big C over little c. If that's the case, then the triangles are similar. And those were our basic similarity theorems, right?
Yeah.
So now our next section is all about area. Now, talking about area is almost identical to the way we talked about length. So let's go back and talk about length for a second. How did we talk about how long some segment was?
Measure it by unit.
Yeah, first we picked some unit. I picked some unit, and I take some segment right there, and I say, there's my unit. My unit is just some segment. And I could call that unit whatever I want. I could call it Bob, or I could call it an inch. And then if that's my unit here, then this right here is 15 bobs or 15 inches, whatever it is.
Yeah.
And what does that mean? It means that we could actually count off that many contiguous segments going off into that. Now, what if your segments don't go into it exactly? What do?
Yes,
Yeah, you get a smaller one, and our general procedure was, we'll then use 1/10 of our unit and make that our new unit. And so maybe, I don't know how many I did, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then some. So this was 10, and then we pick the smaller unit, and we see how many times the smaller unit goes into there. And maybe it went in there 5 more times, but there was still some left over. And so we had to pick some even smaller unit, 1/10 of that unit. And then it might have gone in there 7 times, and maybe it did it exactly. And so it's exactly 10.57 inches, right? So we have a similar concept for when we talk about the area of something. What is the area of this rectangle? How are we going to do that? First, we got to pick some unit. What is our unit going to be this time?
Make it the.
Is it going to be a segment? Are we going to count how many times a segment can go into that thing?
No, you're gonna make it side length. Right?
Roughly, what is the area of this room? Just give me rough ballparks.
I have no idea.
Just super roughly. Who cares? I just want you to say an area out loud.
30 cubic meters.
30 cubic meters for the area of this room?
Area.
What's roughly the area of this room?
I have no idea. How does it make sense?
200 feet squared.
200 feet squared. Or another way you might say that is 200 square feet. Now it's probably closer to 500, but whatever. What does it mean to say that this room is roughly 500 square feet?
There's 500 squares.
It means that if you went and you took this thing, which is a square, that's exactly 1 foot by 1 foot. and you started laying those things out, you could fit 500 of those in this room. Now, not necessarily exactly. So let's pick some unit now. Here's our square foot that we'll say. Here's some bird's eye view of some room, some small room. How many of those squares can we fit in here? So we would start filling this up with squares, and maybe it perfectly goes in like this, creating a grid. With this portion remaining. Then what do we do? Smaller squares. Now, the smaller squares, we're going to do a tenth in either direction. So a tenth and a tenth. Like that. And we start filling it up and see how many of those go in. So how many do I have right here? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So we had 24 squares. But then I start counting how many of those hundreds go in there. And maybe how many hundreds go in there is maybe it's 276 hundredths, count out that thing. So since it's 276 hundredths, that's 2.76. And we would add that to our area there and continue our merry way cutting down to tenths. Now we have a problem using this procedure to get the area of something. It works if our unit, or a tenth of our unit, or a hundredth of our unit, happens to go into these area perfectly. But what happens if it doesn't? And if it's an irrational number? What happens if I've got some area that is 1 by the square root of 2? How on earth am I going to do that? It's irrational. These are not commensurate numbers. Which means that any square I use, if it perfectly goes into this side, its height won't perfectly go into this side. And vice versa, if it perfectly goes into this side, it won't perfectly go into this side. And so it doesn't matter what squares I use, I can never perfectly fill up that rectangle with those squares.
Yeah.
An infinite number of squares, we don't know how to talk about that. Infinity is not a number. What do you mean by an infinite number?
A number of squares that are perfect.
Right, so we're stuck. Someone who has some experience with calculus is already hinting at the notion of a limit. So it turns out you need limits to perfectly define area. We do not have limits in this class, and so we are going to have 3 starting points for talking about area, things that can be proven, but we are just going to take them for granted. Go ahead.
Why not define area as length and width?
Why not define it that way?
Yeah, it seems like that's what.
So you could define the area of a rectangle that way. Length times width. But then that gives you the area of a rectangle. That doesn't give you the area of a triangle. And now you're thinking, because you're used to taking Riemann sums, well, now we can get the area of a triangle. But that's once again using limits. And if we're going to do that, we may as well define an integral. And then we have a definition of area that we get from calculus. So our definition of area comes from calculus. We don't have calculus in this class. We're not going to take limits in this class. So I'm going to list out 3 starting points. All 3 of these starting points are provable, but we're going to treat them like they're postulates. So they are actually theorems. We're going to treat them like postulates. Make sense? We're not going to prove them, but they are provable things.
Why aren't we proving?
Because they require the concept of a limit to prove. They require calculus to prove. It's the job of calculus to give us a well-defined notion of what exactly area is, which we're not doing in this class. But you'll get in calculus. But they're going to be pretty simple and intuitive starting points. Go
How
ahead.
did Euclid define area?
The Greeks were somewhat imprecise with their notion of area. When they referenced a 2-dimensional shape, it was implicitly understood that they were talking about the area. So it's not uncommon to see in Euclid him say something like this is equal to this if their areas are the same. And so it's just understood that when you were talking about some figure, that you meant its area when you were saying 2 figures are equal to each other. So it was not explicitly stated, and they were much more fast and loose with the notion of identity than we are today, and you were just supposed to understand from context what it was he was saying. But it is a very confusing thing if you do ever read Euclid, how he says, this is equal to that. I must be missing something. What do you mean these are equal?
Yeah.
Takes a second to get used to the fact that he just uses words a little bit different than we do. Okay, so what are our starting points going to be? I'm going to start a little bit more foundational than the author chooses to start. So the first thing that I'm going to talk about is, I'll call it Theorem A. This is not one that's in your book. What is Theorem A going to be? It's going to be that if you have a square with side length x, then what is the area of the square?
X squared.
X squared. That is going to be our first basic assumption. Could be proven from calculus, but we're not going to. Okay? Our next theorem. This one now in your book is Theorem 2. I can't remember which order for these next two. Okay, this one is your triangles. So, if this triangle is congruent to this triangle, then the area of that triangle is equal to the area of that triangle. So, triangles that are congruent to each other have equal areas. Should probably specify. So that implies the area of the first triangle is equal to the area of a second triangle. Trying to make this very clear. We're saying that the areas are equal if the triangles are congruent. If we're saying that the areas are equal, what must area be? A number. So keep that very clear in your mind. Area is a number. And here's another way that we're different from the Greeks. The Greeks didn't have numbers in their geometry. And so that's why they talked about the concept in a purely geometric way. It was just implicit in there. So they don't have numbers in their geometry, so they don't have area, the way we mean it today, in their geometry. Make sense? Area, a number. And then finally, the last theorem that we're going to assume is that if you've got some figure, do a dotted line here, the area of this portion of the figure is A1 and the area of this portion of the figure is A2, then the total area is equal to A1 plus A2. So this gives me that. You can calculate the area of one piece of the figure, then calculate the area of another piece of the figure, and add the two areas together, and the result is the area of the resulting figure. That make sense?
Yeah.
So these are three basic starting points. Notice only one of them tells us how to actually calculate area, which is a square with side length x gives you x squared. So initially, if we're going to calculate any area, we got to start by somehow getting squares. You with me? So we'll keep those in mind, and now we'll come and prove Theorem 1 in your book. What is Theorem 1? Theorem 1 is that the area of a rectangle is length times width. Now this is one of the things that your author just takes for granted. I'm going to start with Theorem A and prove that. So I'm starting a little bit more foundational than he is, but just slightly. So we're going to prove that the area of a rectangle is in fact length times width. And we have these three facts to use. Now I'm not going to write out wordy proofs for the proofs that we do today. If any of them you want to see all the words, we can write out all the words. They're going to be largely pictorial, and I'll think you get it from the picture. But we can always do more if you want. So how are we going to start? I'm going to start this with a square. I have to start with a square. Why do I have to start with a square? Because the square is the only figure so far I know how to take the area of. This one doesn't tell me how to take the area of a triangle. It just tells me if I happen to find two congruent triangles, their area is the same. It doesn't tell me how to calculate their area. It just says they're the same, whatever it is. This doesn't tell me how to calculate the area of this figure. It just says that somehow I know the area of that piece and that piece. Then the total area is the sum of them. Well, how do I get the areas of those two pieces? So squares, so far, are the only things we know how to talk about areas of. And this comes back to how we talk about basic units of area. What do I mean by a square foot? I mean a figure that's a foot by a foot. And what's its area? A foot squared. You're counting how many foot squareds go into some room when you talk about its square footage. Okay, so let's start this out. I'm going to make the area of this thing. So let me really quick draw my triangle, the rectangle over here that we're trying to calculate the area of. So here's a rectangle that we're trying to calculate the area of. I'll try to do a somewhat decent picture. with its length times its width. I'm trying to prove that area is length times width. With me? So I'm coming over here and I'm going to draw a square where this is L, this is L, this is W, this is W, this is W, this is L.
Looks similar to how we proved the Pythagorean theorem.
Yes, very similar. And once again, it's not surprising that the Pythagorean theorem is done that way because it's a theorem stating a relationship between areas. Okay, so I've got this rectangle. You gave me this rectangle. You pick any rectangle you want. Once you give me this rectangle, I can come and I can construct this figure, right?
Yeah.
That's pretty straightforward. With me so far? Okay, so now, what is the area of this total square? We'll call this area that we're looking for, we'll call that little a. With me?
Yeah.
Okay, so what is the area of this total square?
Length times width squared. Or length
It
times
is
width.
this distance times this distance,
Right.
or this distance squared. The area of a square is its side length times its side length. That's the area of a square.
Yeah.
So, this is
Length
L
of
plus
the
W.
L plus W squared is its area. You with me?
Yeah.
Okay. Now, the area that we're looking for is the area of this thing right here, I guess you could say. Now, we got to be careful. Is it the area of this thing? Or is it the area of this thing?
Why does it matter?
Why does it matter? How do we know that these two things have the same area? We got to be a little bit careful here. Maybe somehow tipping it on its side changes it. So pretend that here's the rectangle we started with. I just expanded on that drawing, and here's the one we started with. I don't get to assume that it's the same as that one.
Okay.
You with me?
No.
Okay. So now, what's the area of this piece right here? This square right here. You see this internal square?
Yeah.
What's its area?
L squared.
L squared. What's this one's area?
W squared.
W squared. This is the area that we're looking for.
Yeah.
And then we have this figure down here.
Yeah.
Now, what I'm going to do is I'm going to draw a diagonal through this rectangle and through this rectangle. You with me?
Yeah.
I know that this angle right here is, what's this angle right here in this corner? A right angle. What's this angle? A right angle. So I know that this triangle is congruent to that triangle by side angle side. You with me? And I know that this figure is a square, so I know this is also a right angle, and so I know that this is also a right angle. And so let's call A1 the area of this triangle just right there. You with me? This triangle is congruent to this triangle, is congruent to this triangle, is congruent to this triangle, all by side angle side. They all have a right angle and two sides the same length. You with me? So what do I know about the area of all four of those triangles?
They're all the same.
They're all the same. They're all A1.
They're all equal to each other. They're all A1. So I know that whatever the total area is here, it is equal to the sum of all these areas.
Yeah.
So it's equal to L squared plus W squared plus how many A1s do I have? 4 A1s. You with me?
Yeah.
So far, notice that I have used all three of these facts. I have used that the area of a square is square the sides. I have used the fact that triangles have congruent area. That's how I know that that's A1, 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 A1. And then finally, I've used the fact that the total area is the sum of the individual areas. So this total area of this whole square is equal to the area of that, and that, all summed together. So I've used all three of these facts so far, and that's how I'm using them. You with me?
Yeah.
Finally, how does the area we're looking for compare to A1?
Twice as big.
It's twice as big. Now we can say that. Because this is A1, and this is A1, and together we know that they give us the area of the rectangle we care about. So 4A1 is the same as 2A. You with me?
Yes.
Okay, so this is equal to L squared plus W squared plus 2A. No cheating?
Yep.
Expand over here. Do you know how to expand out two terms squared like that?
Yeah. It's L squared.
Let me write it very explicitly, just in case. L plus W squared is L plus W times L plus W.
Yep.
That's what we mean by L plus W squared. How do you multiply this out? You distribute the L to both terms. L times L is L squared. L times W is LW. That's distributing the L to both terms. Now we got to distribute the W to both terms, so it's W times L, WL, or LW. It doesn't matter what order we multiply. And then finally, what's W to W? W squared. So we've got an L squared, we've got two LWs and a W squared. So this over here is the same thing as L squared plus W squared plus 2LW equals that. You with me? Just a slightly different order, combining our like terms. Subtract L squared from both sides, subtract W squared from both sides, and what do I get? 2LW is equal to 2A. Divide both sides by 2, and what do I get? I'm going to write the A first, so the A is equal to L times W. Okay, that's what we were after. Right?
Yeah.
Any questions on that proof? Anything you don't like? No? We're good?
If the starting triangle,
Starting rectangle?
sorry. If you gave it an irrational side length, would you still be able to construct that proof?
Yes. Because, so that's one of the things that we had to fuzz over. If we were only dealing with rational numbers, then we could have always talked about area as some sort of counting process. And we would have been fine. This works for irrational numbers as well. This would have been a proof from calculus and it works for irrationals, and so now we're saved. So, nowhere here did we assume anything special about the rationals. And we just assumed that this works for any square you give me. In terms of any unit you choose. Okay, any other questions? Alright, so our next theorem, theorem 4, is if A and B are the lengths of a right triangle, then the area of the triangle is 1/2 AB. Alright, so theorem 2. So theorem 2 is, thank you, theorem 4. Remember, theorem 2 and theorem 3 are right here. Things that the author aren't going to prove. He doesn't have this. He just takes theorem 1 for granted and doesn't prove it.
Yeah.
So, that's the difference between me and the author. Okay. So here we're going to prove that area of right triangle is 1/2 the base times the height. With me?
Yeah.
1/2 B times A, where B and A are the lengths of the legs. So let's draw out this picture. So I've got my right triangle right here. Any right triangle you choose, I'm going to call that side A and this side B. Just make B at the base. With me so far?
Yeah.
Now our job is to get the area of this right triangle. How can we get the area of that right triangle? We don't know how to take an area of a triangle. What do we know how to take the areas of?
Rectangles and squares.
Squares and rectangles. Do you see somehow how we can get a square or a rectangle we can take the area of?
Yeah, we double it.
If we double it, so if we make that twice as long and that twice as big,
I mean, like.
I know what you mean. We construct a right triangle congruent to this one right here to finish our rectangle. Now we know how to do this process, so let me kind of walk you through the logic of the process. We know that through a point there exists one and only one line parallel to some given line.
Yeah.
So I can make the line through here parallel to that line, and the line through here parallel to that line. You with me?
Yes.
Now, this is a parallelogram, so opposite angles are going to be congruent, so this is now a right angle. Those opposite angles are called corresponding angles, right?
Yeah.
Or opposite interior angles, I guess, is how you would look at it. Where those two lines are parallel, and the cut's going that way if you want.
Yeah.
I think I know what you're talking about.
Okay. So now, there's 100 different ways we can make the argument. So now we've got this over here. First off, it's for sure a parallelogram, right?
Yeah.
So the opposite side of this is A, the opposite side of this is B. To argue that that's right angle, we could probably just think Pythagorean Theorem if that's easier to think about. This has to be C, so this has the same C, so this has to be a right angle. Since this side squared plus this side squared has to equal this side squared, then this side squared plus this side squared has to equal that side squared, and so that has to be a right angle. Because the Pythagorean Theorem holds for right triangles and only right triangles. There's a bunch of other ways we could argue that's right angle. Okay, so we got that that's right angle, we got AB, we got AB. So now we've got this rectangle. So what's the area? Maybe we'll call this area right here A1. Now we're after. What's the area of this piece right here?
Also A1.
How do you know it's also A1?
By
By Theorem 2. Congruent triangles have the same area. This triangle is congruent to this triangle by
side or
side, angle, side. So this triangle and this triangle have the same area. Side, side, side would also work.
how? remind
That's
me
probably
how
an
you
easier
know
way
for
to think
sure.
about it. Forget the right angle. Side, side, side is
Just side, side,
the
side.
most straightforward one to see.
Okay.
So by side, 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 these two triangles are congruent to each other. It's a parallelogram. That's how we knew that the opposite sides were the same length. So parallelogram gives us side, 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 gives us the two triangles are congruent. Now what's the total area of the rectangle? It's A times B. How do I know that? It's AB because of Theorem 1. That's the area of a triangle. But this is also equal to 2 times A1. How do I know that?
Because they're
Theorem 3. Okay. So now divide both sides by 1, or divide both sides by 2, and I get that the area is equal to 1/2. Doesn't matter if we write the B or the A first, because multiplication is commutative. And so our area is equal to 1/2 the base times the height. Make sense?
Yeah.
Okay. Now I'm guessing our next theorem is to do it in general. For any triangle. Unless you have any other questions about that one.
That was Theorem 5 is the area of parallelogram.
Oh, no. Yeah, area of a parallelogram. Okay, this one is pretty cool. And we're trying to do a somewhat decent picture for it. See if I can do it. So we're going to prove try and get these lines somewhat parallel. Just having a slightly decent picture here can help a lot. So we are going to prove that we'll call this down here B. We'll call how high up it goes H. So here is one parallelogram. Let me try and draw another one. I'm going to try and do the same length of segment over here. And then having a slightly decent picture can really help show how this is a little bit surprising. Okay, you see those two shapes?
Yeah.
The slanted one, and then the one that goes straight up and down. Those are both parallelograms. We're going to prove that the area of a parallelogram.
Oh, I love that. You're like so enthusiastic, you guys. Are you learning? I would learn so much from that. Thank you. You missed anybody today.
I think we got everyone.
That is the first class. Thank you, Bear. Thank you for coming to school. I would. Look at that.
Thank you.
Thank you.
All right, so here is a surprising fact. The fact is that both these figures have the exact same area, and the area is just B times H. The base times the height of any parallelogram gives you the exact same thing. And I could have taken this and stretched it even further, and it would have had the exact same area. Seems a little bit surprising, right? I don't know, seems a bit surprising to me. Just looking at the picture, I tried to draw it halfway decent, so it's somewhat accurate. It doesn't scream out to me that those have the same area.
Yeah.
Right? So let's actually prove this. So I'm going to take the more slanted one here, and I'm going to prove that it has the same area as just b times h. You with me? So let's I think these lines might mess up our thinking as we try to do this. Okay, so first thing I'm going to do is I'm going to encompass this parallelogram inside of a rectangle. You with me?
With what, sidelines?
H, whatever the height is. In other words, how do I physically do this? I extend this parallel line right here, and I extend a parallel line right here. And then through there, and that's going to give me the rectangle. With me? Now I'm going to call this distance right here, whatever it is, I'm just going to call it x. I just need to call it something.
Yeah.
Okay, so that's h, this piece is b, this piece is x. Now, so what theorem are we on? 5, thank you. So theorem 5, we are proving that area of parallelogram is base times height. Okay? So here we've got the rectangle set up, so that's very telling. Now, how should we think about this? What's the area of the entire rectangle?
Bx times h. Or b plus x times h.
So the area of the entire rectangle is just the base times the height. What's the base?
B plus d.
This distance plus that distance. B plus x. So b plus x times h is the area of our base.
Yeah.
Now, let's start marking these areas. We'll call A the area that we care about. That's what we're trying to find. I'll call this one right here A1. What should we call that area?
It's the same area.
It's the same area. How do we know it's the same area?
Side.
Side, angle, side. Side, angle, side is one way you could have thought about it. You could have also thought about it as side, side, side. How do I know side, side, side? We already proved that the opposite sides of a parallelogram are congruent.
Yeah.
So I know this side is congruent to this side because they're opposite sides of a parallelogram. Those are the same length. Those are the same length. So by side, 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 they're congruent. Two ways you could have saw it. Both are fine. Okay. So this area is equal to what? The area of the entire rectangle is equal to the sum of these individual components.
Yeah.
So 2a1 plus a.
A plus 2a1, or how you said it was also fine. Now notice, what shapes do we know how to take the area of now?
A triangle. And.
Of right triangles, rectangles, and squares.
Yeah.
We've got that this is a right triangle. We've got that this is a right triangle. And so what is the area of A1?
Is 1/2 x times h.
It's half the base times the height. 1/2 x times h. You with me?
Yeah.
So this is equal to, over here I'm just going to distribute. What's b times h?
bh.
bh. What's x times h? xh. Okay, over here, a is still what we're solving for. Plus, we found out that a1 is half the base times the height.
Yeah.
Good?
Yeah.
All right, let's continue with this. What's 2 times a half?
1.
1 times x
Is x.
times h, x times h. So, over here we get a plus x times h is equal to b times h plus x times h. Now what can I do?
You can
Subtract xh from both sides. And I get, I'm going to write the a first. A is equal to b times h. Exactly what we expected. Right?
Yeah.
Any questions on that? Anything you don't like? Okay, with that, let's prove the area of a triangle in general. So, next theorem, theorem 6. Area of a triangle is 1/2 the base times the height. So far, we only know how to calculate the area of a right triangle. What do we do for any triangle? So now I pick some random triangle here. Trying to make it very clear that it is not a right triangle. Let me draw it a bit bigger though. No, excuse me. Thanks. Okay. Trying to make sure that it doesn't look like a right triangle. Make it taller, I guess. Okay. Hopefully that isn't looking too round. With me so far?
Yeah.
So we're looking to calculate the area of this thing. We'll say that we know the base B and we know the height h. What do I mean by the height? I mean that if you drop an altitude down from here, have we defined an altitude yet?
We've used it.
Construct a line perpendicular to the base that goes through that top point. You with me?
Yeah.
That's what I mean by an altitude. So this we know is a right angle. Then the length of this is what we mean by the height of the triangle.
Is that definition?
An altitude?
The height of that triangle is an altitude. Do we say that explicitly?
I don't know if we've defined the word altitude yet. He probably just says height. The area of a triangle is given by the formula A equals 1/2 B times H using the figure. So H is labeled in the figure. But it will mean the altitude. That's what we'll mean by it. Okay, so what is our idea here for how we can calculate the area of this thing?
The right triangles.
Both of them are returns, yes, you just add them together.
So the only problem is, what's this? We don't know the base of this thing. We don't know the base of that thing. How can we do it? So I seem to be getting a little stuck there. Any other ideas? What did we do over here, first step?
Construct the rectangle.
Constructed the rectangle that contained it. What did we do here, first step?
Constructed a rectangle.
What did we do here, first step?
Made a square.
Constructed a square. So
It's probably, yeah. So
Wow.
probably one
Construct
to start
square.
with.
So it's very useful to construct some container that we know how to calculate the area of. So what's a container we can construct around this that we know how to calculate the area of?
Rectangle.
A rectangle is very strongly being hinted at by this figure, I think. So let me, I don't know if we should just draw it or try and give you the proof idea, or the idea. So how would we actually construct that rectangle? Take the line through here, parallel to this thing, right?
Can I step out?
Yeah, go ahead. And then we could construct a perpendicular to this line at this point. That's a construction we've already done. In fact, I think that was on your test. Not the actual construction, but prove that given a line and a point, there's one and only one line through the point perpendicular to the line. So this point happens to be on this line. Nonetheless, there is that perpendicular that comes up. And we can look at where it intersects there. We can construct the perpendicular here. Look at where it intersects there. And we get our rectangle. Okay, so now we've got our rectangle. All right, did that help us any?
Yes.
We know the area of the total rectangle. What's the area of the total rectangle? H times B. Or I'll do B times H. That's usually the way we think about it, right? Base times height, just to put the order a little bit more nicely. And now, what is the area of this total thing? Let's look at the component areas. So I'll call this piece over here A1. And I'll call this piece over here A2. And we're looking for A1 plus A2, right? That's the area of our starting triangle that we had. Good? Okay, so we got that. What's the area of that chunk right there? A1. How does he know that this is A1? Side angle side. Because this length is also going to be H. This distance is also going to be B. And this is also a right angle. So by side, angle, side, this triangle is congruent to that triangle. Similarly for this triangle to that triangle. So this is also A2.
Is that side going to be length B? I thought the entire bottom side was length.
Oh, you are correct. So if we wanted to call this piece right here little x, we could call this b minus x, then this is b minus x, and then that is x. But what the actual length is, we don't care about. The point is that and that have the same length, that and that have the same length because it's a parallelogram. And you could even use side, side, side if you wanted. However you want to think about it, but the point is, this triangle and this triangle, same area. This triangle and this triangle, same area, right? So what's the total area?
It's 2A1 plus
2 times A1 plus 2 times A2, right? I'm going to factor the 2 out of both those terms, and so this is equal to 2 times A1 plus A2. With me?
Yeah.
What is A1 plus A2?
It's the triangle.
That's the area of the triangle we're looking for. So then, over here, we get A1 plus A2 is equal to what?
2 times.
We divide both sides by 2.
It's 1/2 base times height.
If base times height is equal to 2 times A1 plus A2, then dividing both sides by 2, we get A1 plus A2 is equal to 1/2 the base times the height. Do you see it?
Yeah.
So there's the area of the triangle. Now, we kind of cheated. How did we cheat? We kind of assumed that this point was somehow above this line segment. Let me draw another triangle and kind of show you how we could have quickly gotten into trouble without being careful in our thinking. If we had this triangle, now our height is this distance. And so now, we can't just construct that same rectangle. Now it would work if we flip this, use its longest side on the base, and redone our proof. That would work. So this proof always works as long as you choose your base to be the longest side of the triangle. Then that works. But we don't want to always have to use the longest side of the triangle. That's too much thinking for us. So let's see if we can prove it without having to think about the longest side of the triangle. With me? So we're going to start with a picture like this. First thing I'm going to do is I'm going to come up here and I'm going to construct a line through there parallel to the line down here. With me? Now we'll call that B, and then we know that the height of the whole thing is, what's the height of the whole thing? H. So there's our base, there's our height. I'm trying to prove that the area of this skewampus triangle is 1/2 the base times the height. This time what I'm going to do is I'm going to come up on this line and mark off a segment congruent to that one. You with me? And then I'm going to let this line come down like that. With me? So I know that this side is congruent to this side. It's a parallelogram, so this side is congruent to this side, and that side's congruent to itself, so side, 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 this triangle is congruent to that. So we'll call this one A1. Whatever the area of that one is, it has to be the same.
Yeah.
Now what is the area of the entire parallelogram? So the area of the parallelogram is just base times height. That's what we proved in this picture right here, or up at Theorem 5. So base times height is equal to 2 times the area we care about, which gives us that the area we care about, A1, is just equal to 1/2 the base times the height. It is simpler, but this one is probably one that if I left you alone in a room, you would come up with this one. So that one has less steps, and that's the reason that this theorem instantly followed after our one with a parallelogram. So that was Theorem 6. All right, we'll move the camera, move on to Theorem 7. By the way, nice simple day today.
Yeah.
We're mostly done already. So you got an easy day ahead of you, which is good.
Pythagorean Theorem.
I'm dead.
You're dead.
I had a baby last night.
Oh.
I've not slept yet.
Still came to school.
You think I'm going to let you off that easy?
So it's priority.
Is the next one just Pythagorean theorem? Okay. Yeah, so this is a very pictorial, area-like picture of the Pythagorean theorem. We've already proved the Pythagorean theorem once, but now let's prove it thinking about in terms of areas. What is the Pythagorean theorem? The Pythagorean theorem is, give me a right triangle, any right triangle. Call this side length A, this side length B, this side length C. Then the area, using this, the area of the square, using A, plus the area of the square you would get constructed at this end. Sorry, that was not even close to looking like a square. B is equal to the area of this square, which is going to go off my screen here because I didn't think ahead very well. So we're going to prove that this area, what is the area, put the A here, the B here, the C here. What is the area of this square over here?
A squared.
A squared. The area of this square?
B squared.
B squared. The area of this square?
C squared.
C squared. So we're going to prove, this is another way to think about the Pythagorean theorem, that A squared plus B squared equals C squared. Very surprising fact. So here's the way that we're going to prove it. We're going to construct the same square two different ways. So I'll try and kind of make it match up with that. We'll see how good I can do. So I'm trying to do like I'm trying to make that roughly the same big as that, and then we need this roughly the same big as that. So let me try that again, something like that. So if we use that, really helps see it if I can keep these, keep my picture somewhat accurate. All right, not a perfect picture, but I'm trying to construct the picture so that this distance is A, this distance is B, and then if we were to go up, this distance is A, this distance is B, and then try and take that, come over, A, B, B, A. With me so far?
No.
Now, this square is meant to be the same big as this square. So again, I'm trying to do A here, trying to do A here, trying to do A here, and trying to do A here, and then this would be B. That was A, B, A, B, and that was B. And now I'm going to connect these points. This right here is a right angle by design,
Yep.
right?
Yep.
So if that's A, that's a right angle, and that's B, what does this side have to be? Has to be C, because this triangle is going to be congruent. Here's the triangle I started out with. So I start with that triangle, and I'm trying to prove that this square plus that square equals that square in terms of area. Okay, so that's a right angle, that's C. Here's a right angle, this is C. Here's a right angle, this is C. Here's a right angle, this is C. With me so far? Now, you need to quickly make an argument that this right here is a right angle. I'm going to call this angle right here angle alpha. I'm going to call this angle right here angle beta. Now, first off, this triangle is congruent to this triangle. How do I know?
Just side angle side.
Side angle side.
Side.
So this angle, also side, side, side. But so this angle also has to be alpha. If that angle is alpha, that angle has to also be alpha.
Yeah.
Similarly, this has to be beta, and I could go through labeling all these angles alpha, beta, right?
Yeah.
Now, we're going to use a degrees type argument just to help you see it. We don't have to, but I just think it makes it the most intuitive. So alpha plus beta plus 90 degrees equals alpha plus beta plus a right angle 90 degrees is equal to 180 degrees. Or in other words, the angle sum of a triangle is a straight angle. Now I may call this last angle over here, call it gamma. What does alpha plus beta plus gamma have to equal? Equals a straight angle, 180 degrees, right? Now, looking at the top equation, if alpha plus beta plus 90 degrees is 180 degrees, what is alpha plus beta? 90 degrees. Because alpha plus beta plus 90 degrees is 180. So subtract 90 degrees from both sides, and I get alpha plus beta is 90 degrees. That's from the top equation. You ready?
Yeah.
Substituting that into this bottom equation, what's alpha plus beta then? 90 degrees. So 90 degrees plus gamma is equal to 180 degrees. Subtract 90 degrees from both sides, and gamma is equal to 90 degrees or a right angle. Now we could have made that argument with right angles or straight angles, but it's a mess. So, this angle right here, all that work to set this angle has to be a right angle.
Which means that all the other ones are.
Which means that all the other ones are right angles, or more importantly, this inner figure is a square. That's all we were trying to argue. And that's kind of the hard part of the proof. So now, let's calculate the area of these things. So I know that the area of this and the area of this have to be equal.
Yeah.
How do I know that?
Because they constructed it that way.
The same square.
Because they're the exact same square, right? Their square is side length
AB.
a plus b squared.
Yeah.
So let's look at it for this square. A plus b squared. Let's really quick prove that that distributes the way that you know and love. Here's Euclid's way of proving it. What is a plus b squared equal to? Well, let's look at it. Here's a plus b as a square. A plus b squared. What's the area of this piece? A squared. What's the area of this piece?
AB.
A times b. What's the area of this piece? B squared. What's the area of this piece?
AB.
A times b. And so Euclid wouldn't have done the algebra here. He wouldn't have distributed. He would have made this construction and said, what is a plus b squared? Well, let's see. It gives you an a squared. It gives you two of these ab's. And then it gives you this b squared. That's how he would have proved that a plus b squared is equal to a squared plus 2ab plus b squared. No distribution required.
Yeah.
Because he didn't have those algebraic rules. All the algebraic rules you have for distribution, Euclid would come up with some construction that did that thing. Now this also has to be equal to the area over here.
Right.
Now the area over here, what do we have? We have 4 of these triangles that all have the same area. So we have 4 times the area of one of those triangles, right?
Yes.
What's the area of this triangle right here? It's a right triangle. What?
1/2 AB.
1/2 AB. 1/2 the base times the height. That was clear back over there in Theorem 4.
Yeah.
Good? And then we miss this inner piece. What's the area of this inner piece? C squared, because it's a square of side length c. That's what c squared means. So plus c squared. Now 4 times 1/2 is 2. So this is a squared plus 2ab plus b squared is equal to 2ab plus c squared. Subtract 2ab from both sides, and I get that a squared plus b squared is equal to c squared.
Would Euclid have done the final algebra steps then?
He would have talked about how this figure and this figure together are that figure, and this figure and this figure together are that figure. And so this figure and this figure together have to be this figure. That's the way he would have talked about, but it's the same type of thinking.
Right.
But that's worth noting. Yeah, good. Okay, so that was Theorem 10.7. And one more, not a proof, but a construction, a neat construction. Hopefully I can remember how to do this. So here's the problem that's given to us. We're given some random trapezoid. We've got to draw the trapezoid so that we don't assume too much information. No 2 sides parallel. We're not going to use the nice trapezoid that you all know and love where you have 2 parallel sides. we need to draw any four-sided figure. Not trapezoid, quadrilateral. Trapezoid means two sides are parallel. Any quadrilateral. So I'm going to draw some ugly quadrilateral that tries to make it as hard to work with as possible. So here's a quadrilateral that we're going to draw. Right? Very ugly one. Not a lot of nice properties that that thing has.
Yeah.
Right? Pretty ugly. We don't like it. What is our job here? Our job is to construct a triangle that has the exact same area as that thing. So you're some architect laying out a design for a temple for me. I say, love it, perfect area, just make it a triangle. Don't mess with the area. But I want the shape now to be a triangle. Pretty contrived scenario.
Yeah.
It came up a lot in ancient Greece. All their triangle temples that they have. Okay. So, how on earth do we do this? Now, how on earth do we do this?
Take a line from.
We need to flip, triangle. Okay, I think I see it. I need to look at it, how I'm going to get my parallel lines. Sorry, that is useless information to you. Okay, maybe keeping the lines halfway straight here will help me do decent. First off, let me extend this out. See if I can without making it hideous. We'll need plenty of space out, eh? So extend out that base because I'm going to construct my triangle this way. And it's going to have this side, one of the sides shared. I'm going to have it share this side, going this way. Okay? So we already have this side of the triangle. Some distance I need to go this way so that when I construct the triangle, it has the same area as this thing. Now, I'm going to construct a line. And I don't want to mess too much with my picture here so that you can see the original picture. So I'm going to try and do it as a dotted line. And that's meant to go from this vertex to that point. You with me?
Yeah.
Now the hard part. I need to draw a line parallel to this line that goes through that point.
Okay.
So that's where hopefully this bad boy will help me out. Does that look pretty good?
That's all right.
Yeah.
And the hardest part is figuring out where your chalk is going to hit. Okay. Hopefully that's clear enough for our picture. You're going to need to be able to see the parallel lines to see the proof I did. Okay, so it turns out, one more line out for our triangle, to finish off our triangle. Ooh, that looks kind of weak. Sorry about that. Okay. So now, let me label some points just so that we can talk about stuff. Let's call that point A, B, C, D, E. Okay, so I'm arguing that triangle ABE has the same area as quadrilateral ABCD. You see it?
Yeah.
Okay, so notice that this portion, using the dotted line going here to here, both figures have.
Yeah.
So I'll call that portion, I don't know, A. So they both have that area. So maybe, just to be super clear, let's try and shade it in so that we don't forget exactly what it references. Okay, that's it. What remains to be argued is that this triangle, BDE, has the same area as this triangle, BCD. If the remaining portion of the quadrilateral has the same area as the remaining portion of our triangle, then we're done. You with me?
Yeah.
Now, the hardest thing to get on here is the height between these two parallel lines. And if we can make that appeal to your intuition, I think that this will be fine. Okay, so H here is the distance between these two parallel lines. Does that look like it's perpendicular? Maybe
Yeah.
slanted more? Okay, call that distance right there h. Now, tilt your head for me. Looking this way, we've got this triangle where its base is right here, the dotted line. And we've got this triangle where its base is this dotted line. And they both have height h.
They do? Oh, yeah, they do.
Maybe it'll be easier. I'm going to cut that thing and I'm going to redraw over here. This will be easier. And then we don't have to try so hard to make everything look perfect and you'll just be able to see it. So this base, BD, I'm going to come, throw it up here. This is B, this is D. C is somewhere up right here. Here's C. And then E is somewhere shooting off over here. Here's E. So we're looking at these two triangles. Not a perfect drawing, but when it's lined up with how you want to look at parallel lines, it just helps a ton. And the height here is h.
Gotcha.
The area of this triangle and this triangle are the same. What is the area of triangle BCD? It's its base times the height, times 1/2. And what is the area of this triangle right here? It's 1/2 its base times its height. Since they have the same base and they have the same height, they have the same area. So looking sideways, triangle BDC and BDE, looking at these as our parallel lines, have the same base and the same height.
So they have same area.
Right, so if this is A1, then this is A1. And so the total area is just A plus A1 for this figure. A1 here, both of these reference this middle piece right here. Right? So A plus A1, the area of the trapezoid, is equal to A plus A1, the area of the triangle.
The quadrilateral you said trapezoid.
Yes. Thank you.
Does that work for
Any quadrilateral.
Does that work for any polygon with any number of sides? Or does it have to be quadrilateral?
This works with the quadrilateral simply because you could probably come up with a recursive way to make this work,
Yeah.
thinking ahead. So I'm not positive. Let me just kind of play with the idea. Let's kind of draw a multi-sided one with the same idea. So there's some polygon with a bunch of sides. I could kind of ignore that. I could view it as 1, 2, 3 with that. Construct the triangle. Maybe it doesn't
You could,
work like I'm thinking.
You could take it down. You could separate it into a quadrilateral and then construct a triangle off of it.
Yeah, we could find the triangle that matches that area.
And then find the quadrilateral.
So there's our quadrilateral. 1, 2, oh no. So here's our first quadrilateral. 1, 2, 3, 4. I can find the triangle that matches that thing. Now I somehow need to add that area on to it.
Well, that could be the two triangles at the bottom or another quadrilateral. Okay. 1, 2.
That's true.
So that.
But then I need to somehow add two triangles together to get a quadrilateral, which is weird. I feel like there should be a way to do it.
So maybe not express it as a triangle, express it as some kind of lower polygon that has left sides.
But when you remove one of the sides, you start cutting out pieces of area. And you need to make sure you recapture it.
Right.
So I feel like there should be some recursive way to go about doing this.
It seems like it was like a graph theory.
I mean, there is always a way to actually do it in terms of using lengths.
There it is.
Yeah, because you can always just calculate the area and then construct the triangle you want that gives you that area. But this is just a way that a Greek would have done it, since they don't have the concept of using numbers in terms of how they do it.
And you can't do it with a circle.
You can't do it with a circle. Sure you can.
You can create a triangle that has the same area as a circle.
That is very easy construction to do. So here's your circle with the radius r, whatever r is. And then its circumference is whatever its circumference is. Well, I guess the hard part is figuring out how exactly you get your circumference.
What is that?
But if you could easily get your circumference, it's just going to be c times r is a triangle.
Oh.
Because c is 2 pi r. And so you do half the base times the height gives you pi r squared. So the hard part there, I guess, is constructing the circumference, and I guess doing that with a ruler and straight edge. I'm not sure you could do that. So
You can't.
I thought it was too simple.
You can't construct a square that has the same area as a.
So yeah, what you're thinking about is I give you a circle. I want you to construct a square that has the same area as that circle. And yeah, you must be right, because if I could do this, I could easily get that square.
Oh, 1/2
So,
radius.
yeah, so I guess the problem here is we can't construct pi. So you're right. I thought that was kind of straightforward because it's just circumference times r, but getting the circumference as a construction, that's where we're going to get stuck.
Impossible. That actually makes sense. You have to kind of unwrap the circumference.
Yeah, I would think it's possible, but I'm not positive.
Well,
Because here, it would be getting the square root of pi. But if you can get pi, you can get the square root. So yeah, it must be impossible. Because to get the square root of pi,
Well, you have to get pi.
right, if you got pi, getting the square root is easier. So, yeah, that's going to be impossible. And the way you get the square root of pi from pi is geometric mean. Where at the triangle of 1 and pi, the geometric mean of 1 and pi is the square root of pi. So, I think you're right. Any other questions? All right, that's it for today's lecture. Areas, pretty fun. Nice pictorial lecture.
Yeah.
I like it.